Greetings, everyone. All right, here are some things on antiderivatives. First thing I want to remind everybody, we first started learning antiderivatives was back in section 4.9, before we ever got into the integration section. And the idea of taking an antiderivative was just reversing the process of taking a derivative. And so that's why our first technique was always to see if we recognize the integrand as the derivative of some known function. But one thing that we added to it, because when we take an antiderivative, we get this family of curves, is this notion of the plus c. Don't forget your plus c. I wrote a little the word plus below the plus symbol in case it looked too much like a t, but make sure when you take an antiderivative, you write your plus c. Otherwise, especially in the free response questions, if you're doing a separable differential equation problem, you are going to lose most of the points. Literally, the max you can get, at least on the ones we've seen in the past dozen years, are 2 out of 5. You can't get anything more than that without the plus c, and that's assuming that you also separated the variables correctly and found correct antiderivatives. And so plus c becomes very important. During the multiple choice section, much of the time, if you're just finding an antiderivative without any particular, just a general antiderivative, not a particular solution, then the plus c is already in the answer selection, and so it's not much you have to think about. But if they actually ask you to find a particular solution, meaning solve for that constant, to find the equation that has no c in it, but a number value instead, then if you don't put the plus c and actually solve for it, you'll get a wrong answer choice. All right, so plus c is important, so don't forget that. Then again, like I was saying, we pretty much have to just recognize when we're finding an antiderivative. So if I, for instance, and an easy one is to find the antiderivative of cosine of x. Well, we know the derivative of sine x is cosine of x, so this is going to be sine x plus c. And so, again, we first use the process of recognition when possible. Then we reverse the power rule. That was another early technique that we had. And so we would, add 1 to the exponent, divide by that new exponent, of course, plus c. And that was another one of our early techniques. But those techniques didn't last too long. They didn't do a whole lot for us, or give us a whole lot of capabilities. Pretty quickly we had to be able to adapt. Now, of course, we do have the constant multiple rule, which I guess I can list it for a moment. The integral of c times f of x with respect to x is just c times the integral f of x dx, and then sums and differences. We didn't have a product rule for antiderivatives. If I'm multiplying two functions together, I cannot just separate them into two separate integrals and multiply the results together, or quotients either. That doesn't work. Okay, so that was never something we even attempted. Lost my train of thought there for a moment. Okay, so after that, we had to start adopting some other strategies, and the next strategy that we had was algebra. So we'd be given, some finding an antiderivative of something that looked like this, maybe x cubed plus x over the square root of x dx, and we have to work something like this out. And so some people try to make it too complicated, and maybe even after we learn u substitution, we'll try a u substitution here or something like that, which is not necessarily going to fail, but not the most effective way of doing this. If you just remember some algebra here, I can separate this into x cubed over x to the 1/2 plus x over x to the 1/2, and then of course dx. And from there, I can just use my laws of exponents to reduce, and this becomes x to the 5/2, 2.5. If you take 3 and subtract a half, it's 2.5, but that's 5/2 as a fraction. And then plus x to the 1/2, and then just from there, reverse the power rule and work it out. So we saw this, for example, on at least the AB practice exam. I'm not sure I don't remember if it was on the BC or not, but we had something to the effect like x squared plus x squared dx, and we needed to find an antiderivative for this. And some people wrongly thought the answer choice was going to be 1/3 x squared plus x cubed plus a constant. And that doesn't work because if I actually take the derivative of this, okay, so then the 3 and the 1/3 multiply out, and I get x squared plus x squared, and you think, oh, we're there, but we have to apply the chain rule, and we take the derivative of that inner function. We have to multiply by 2x plus 1, and therefore this didn't work. Okay, this is not the way you're supposed to handle this. What we're supposed to do is just multiply this out, and then go from there. So I'd have an x to the 4th plus 2x cubed plus x squared dx, which I'll just squeeze right there, and then just integrate term by term. So you have to be careful on recognizing the proper tool to use. If you wanted to attempt something like this problem here and get an answer that looks something like this, you have to think in terms of some u substitution. But a u substitution on that problem doesn't work, because if I'm going to let u equal x squared plus 1, I'm going to end up with du equal to, x squared plus x. I'm going to get du equal to 2x plus 1 dx, and I don't have a factor of 2x plus 1 in my integrand, and so u substitutions don't work, or the substitution does not work in this case. Now, if you want to write a new problem where we'd have x squared plus x quantity squared times 2x plus 1 dx, and then do this substitution here down on this one, then this would work, because then I'd just end up with the integral of u squared du, and then we would get the 1/3 u cubed plus c, and then I could substitute in and have 1/3 the quantity x squared plus x to the 3rd power plus a constant. In that case, it would work. So just be careful. Make sure that if you see an example like we had e to the root x over root x dx, because we have a root x in the numerator, we're going to let u be root x, and we'll end up with that factor in the denominator as well. Another example is something like sine of root x over root x dx. It's the same problem, just instead of using the exponential, we're using sine. So if you want to practice, do a u substitution letting u equal root x in either cases, and you'll be able to work those out. Now, a couple of things briefly on the fundamental theorem. Okay, so remember the fundamental theorem says if we take the definite integral from a to b of f prime of x dx, then I take an antiderivative of f prime, which is f, and I plug in b, plug in a, and subtract. Okay, and so another notation that you might do in between would be, well, that's sloppy. F of x, sloppy again, but I'm going to let it go this time, evaluated from a to b. Once we actually take an antiderivative of the integrand, we get rid of the integral symbol. Okay, so you could put in the intermediate step of putting the brackets around the antiderivative, including the b and the a, and then going into the subtraction step. That's what this step means. But I've noticed some people still leaving an integral symbol on after they've taken an antiderivative, and that would not be a correct technique. So this fundamental theorem, as we saw, comes up quite a bit, and you just want to make sure that you're comfortable in all the different ways that it comes up. We can solve this equation for, say, f of b, and get f of b is equal to f of a plus the definite integral from a to b of f prime of x dx. And that's one way that we've used this quite a bit to figure out what the value of a function is at some later point, knowing the value of the function at an earlier point and its rate of change, so that we can integrate the rate of change over some interval to get a quantity. Oftentimes, we see, especially in calculator sections, that this is done with a calculator, that they give you a function where you cannot find an antiderivative by hand, and you have to just generate the value on the calculator. and then add to it whatever they give you for the value for f of a. Comes up a lot. Comes up a lot. Make sure you're prepared for that. Look at those examples from the practice exam, because they came up a lot on that, and or that sheet that I gave you that had this stuff explained on it a while back. That we had the quiz that was based on that. So study that stuff. I'm going to continue on for some BC topics. So if you're an AB student, that would be pretty much the end of this video for you. But I'm going to go a few more minutes for BC. For you BC students, let's remember we have some additional things to consider. Okay, when we're taking a definite integral from a to b of f of x dx, you have to check to make sure that it is proper and not improper if you're going to apply the fundamental theorem. Okay, f must be continuous. So f must be continuous on the closed interval AB if you're going to apply the fundamental theorem. So if you're going to take an antiderivative for f and then plug in b, plug in a, and subtract, make sure you check that the function is continuous on that interval. Otherwise, it is improper, and there's a different technique for handling it, as we handled in section 5.10, you're setting up the limits and whatnot. So please be aware of that. Also remember that the upper lower limits both have to be finite numbers. If either of those are infinite, then it automatically is improper. But we haven't had trouble recognizing that. The problems that we've had has been recognizing and checking that the integrand is, whether or not the integrand is continuous. Some other things that we've had to deal with in BC that are not part of AB curriculum are integration by parts, which I'll just abbreviate here, integration by parts, and then we have partial fraction decomposition, and then trig substitutions. Okay, and so I'm not going to go through all of those here. I'm just trying to remind you that those are important parts of the BC exam. They come up a lot less. They want more application. They want more of the series stuff. They want more of logistic differential equation, arc length, parametric equation, vector stuff, and all that. So all that stuff is going to have to come up and be dealt with. But these things will come up a little bit. We don't see them a ton, but familiarize yourself. Remind yourself of the trig substitution. Go back and look at your notes and some examples. Partial fraction decomposition, I think we've been doing pretty well with. So you'll need to spend a ton of time on that if you're comfortable with it. And then remind yourself of integration by parts a little bit. Remember, though, the integration by parts is not one of your first techniques you check. Check U substitution first before you check integration by parts, and really see if it can be worked out using a simpler technique. But it won't always be able to. All right, so go back and take a look at your notes, look at some practice problems, and prepare yourself the best you can. Go study.